to whip up Mathematica programs, and here's the picture of the zeros of the orthogonal polynomials. In this case, you indeed see that they're doing a very good job of converging to uniformity, to a uniform measure on the circle of radius a half. But in fact, there's something much more striking in the picture. It's not merely uniform, it's almost too uniform. There seems to be a strict asymptotic spacing. The zeros look like the numerals on a clock, and so that's when I started referring to this as clock behavior, because at least in this circle case, where it's a circle, it looks like a clock. Of course, when we're looking at the real line, it's no longer a uniform clock. There's no circle to be on. There's a line, but it's not strict equal spacing globally, because, in fact, if there were equal spacing globally, the density of states would be Lebesgue measure, and the density of states, which I remind you is defined as the limit of the counting measures of zeros, converges not to Lebesgue measure, but to a multiple of Lebesgue measure. And typically in the orthogonal polynomial realm, the measure d rho is a potential theoretic equilibrium measure. For the case of an interval, that's not the Wigner semicircle, it's the upside down semicircle. It appears in the denominator rather than the numerator, the square root. And to describe what I mean by clock behavior, I'm going to label the zeros. I'm going to pick some point x, and I'm going to label the zeros. There should, of course, be two labels, one depending on the degree of the polynomial and one depending on the zero. But I'll implicitly, there's an n here also, and I'll label the zeros in numeric order centered about x. And by clock behavior, I mean that the spacing between zeros, when n is large, goes like 1 over n. And at least if this is strong enough convergence for the density to work out right, it has to go like 1 over this density rho of x times n. And the striking thing, of course, about clocks is that the spacings are equal. And as I'll try to explain later, there can be some potential cases where the density of states doesn't even exist, and you can still have equal spacing. And so that I'm going in this talk to call weak clock. In the actual paper with Avila and Last, we call it quasi-clock, because Yoram and I made the mistake of using the term weak clock in an earlier paper for something else. And for publication, I lost the argument, but since I'm speaking here, I would have preferred saying, forget about the fact that we use this definition differently elsewhere. This is what one should really mean by weak clock, but instead it's quasi-clock. But it's really just discussing the equal spacing and doesn't require the spacing to, when multiplied by n, have a limit. And I also want to remind you, at least for the interval -1, 1, the density has this anti-semicircle, upside-down semicircle behavior. So the history, if you look at the zeros of the class of polynomials known as Jacobi polynomials, which includes Legendre, but also Chebyshev of the first and second kind and various other things, the asymptotics of the zeros is quote-unquote classical. Probably only goes back about 100 years, but it's, for example, in Zago's famous 1939 book, he discusses the zeros. And there's a very important paper by Erdos and Turan in the Annals in 1940. They were actually the first people to prove the existence of the density of states on a large class of orthogonal polynomials on the interval. They also had something on clock behavior in many cases. There's a very important contribution that was overlooked by many years in the very last few sections of Freud's book on orthogonal polynomials. I'll talk a little bit more about that in a moment. And without actually knowing about Freud's contributions, I began looking at these things. I have a series of papers starting in 2005, and in particular, one of them was with Urim Last, and we proved that if you have a sequence of Jacobi parameters, a Jacobi matrix, where the diagonal elements Bn are going to 0, the off-diagonal elements An are going to 1, and if there was a bounded variation condition, then you had clock behavior. And Lubinsky, in 2007, found a totally new approach to universality. I'll remind you what I call universality. It was called something else yesterday. Without really realizing that this was connected with zeros, he has a beautiful approach that I'm not going to discuss because he didn't like something about it and found an even more interesting approach that I will discuss. This paper will appear shortly in the Annals. And then with Levin, he used it to look at zeros, and Levin essentially rediscovered this argument of Freud that I'll mention in a moment. And then CALTECH and I pushed Lubinsky, who could deal with a single interval, to multiple intervals, but one always needed open sets in the support where you could say something about the measure and the zeros. And in 2008, Lubinsky found a different approach that I'm going to discuss. It's a second way of looking at this universality. And then Avila Last and I, using his second approach and a lot more, applied this to the context of absolutely continuous spectrum of ergodic Jacobi matrices, where typically the spectrum is going to be some kind of Cantor set, or often it will be a Cantor set, and therefore the earlier methods that require open intervals inside the support won't work. So I'm going to, just for notation, I'm going to have a measure whose essential support is some compact set E. The weight is W, and there's a singular part in general. The PNs will be the orthogonal polynomials. So these are, the little pn means they're normalized. So they're the normalized eigenvalues in the boxes with the right boundary conditions. And one often looks at the so-called Christoffel-Darboux kernel, or reproducing kernel, which is this averaged weight. And traditionally, one puts the complex conjugate on the left-hand side, although probably it should have been on the y. And there's a wonderful formula that you get from Wronskian considerations or other ways that tells you that this sum can be written in this combination. And I want to note something important about this formula for later purposes. Namely, suppose that y is picked to be a 0 of Pn. Then it's not a 0 of Pn plus 1, because you can show the zeros interlace. And when does this side vanish? When Pn of y is 0, as a function of x, it vanishes exactly at the zeros of Pn of x, except, of course, when x equals y, because the denominator then makes this not vanish. Now, universality is the statement that yesterday was described as the Wigner-Dyson sign formula. I think Freud probably discussed this kind of behavior before Wigner and Dyson, and one of the things that I'm still quite puzzled about is the connection between what I'm saying here at some deep level and the random matrix behavior. Of course, in the random matrix behavior, the object you're looking at is some averaged, not individual things. And so you get very different information about the zeros. As we'll see in a second, this is going to imply clock behavior. And of course, in the random matrix case, we don't have clock behavior, but we still have the sign kernel, and I haven't quite figured out how to understand that fact. This is proven for Freud with orthogonal polynomials on the interval -1, 1 when the weight W is very nice. Was there a question I could?
I just couldn't see something.
Ah, okay.
Yeah, so this relation was proved in Freud.
This relation was proven in Freud with the specific row of x being this 1 over square root, etc., that happens for the interval -1, 1.
Barry, I also wanted to ask, are you going to write the equation you are discussing all the time? Because there has already appeared an at some point, and what is an?
I probably am not writing the equation, so
Yeah, I think it is just for the.
I'm taking a standard Jacobi matrix, and this is associated with the underlying measure d mu. These are the recursion coefficients for the orthogonal polynomials.
So under what conditions did Freud prove this again?
It's fairly smooth, fairly strong global regularity conditions on the weight on -1, 1 and smoothness.
Then you take your orthogonal polynomials with respect to that and form this kernel.
Correct. And he proves this result. And he used it, by the way, then to prove a clock behavior on the zeros. Using random matrix, so the same object, not quite the same object, a very similar object appears in random matrix theory. The difference from what I'm talking about in the random matrix application is in the random matrix application, the underlying measure d mu is not n independent. It's n dependent. It has an e to the n v of x or n something of x in the numerator, and as you change n, you not only change the degree of the polynomial, you change the underlying measure. And I'm talking here about the case where the measure is fixed. And Lubinsky has applied his ideas to this case of n-dependent weight to recover some of the results that were obtained in that case. The random matrix people originally did it in this n-dependent measure case, but then somebody bothered to say, oh, what happens if the measure isn't n-dependent? And so this result, without knowing about Freud, was recovered by Arno Krulaz and one of his students for analytic weights. Much stronger hypotheses than Freud. And Lubinsky found this in his first approach, this wonderful, elegant way of doing it on an interval. And then, as I said, found the second approach that I'm going to discuss. And I want you to note that because the zeros of the sine function are exactly equally spaced, you will not be surprised that universality can be used to prove clock behavior. This is explicitly in Freud. Lubinsky and Levin rediscovered this, and Lubinsky later said, oh yes, I remember it was in Freud, but I'd forgotten that. And so I've taken to calling it the Lubinsky-Freud theorem. Sorry, not Lubinsky, Freud. Freud-Levin theorem. At least this half violates Arnold's principle. Arnold's principle says that nothing in mathematics is named after its inventors. And there's Berry's principle, which says Arnold's principle applies to Arnold's principle. So I'm going to talk for a second. I want to emphasize that often one is interested in what I'll call modified universality. So one can define an approximate, quote, density. You take this kernel W of x, Kn of x, divide by n, you call that rho n, and it's a general fact that was emphasized by Freud and Navai. Navai has a long paper dealing with attempts to prove this and actual proofs that in general this approximate rho n does converge to the underlying density, and that it's connected to the density of states. There's a result I showed that in fact this object multiplied by, forget about the w of x. Without the w of x, you multiply by the measure. So the absolutely continuous part of this measure is that actually converges weakly in the sense of measures to d rho. This is in fact just a rephrasing of the result that Avron and I proved 25 years ago about the independence of the density of states on boundary conditions. This Kn is in many ways the free boundary condition density of states as opposed to the Dirichlet boundary condition, which is counting zeros. And modified universality just puts things in the other way around. If the rho n's converge to rho, this is equivalent to what I called universality. But it can happen that the rho n's might not converge, and this still holds. And this still implies weak clock behavior, because this doesn't say anything about the spacing of individual zeros, but because on the local level, which is given by the rho n, you get equal spacing, you do get this weak clock behavior. And again, if the rho n's converge, and in all the cases we actually know they do, you get it. And in fact, the random matrix people, because their rho n doesn't converge without a slightly different normalization, usually write universality in this way. And as I said, modified universality implies weak clock. And I actually believe there's a conjecture in the paper of Avila, Last, and Simon that says almost everywhere on the AC part of the measure, one has this modified universality, no regularity conditions, and that would imply weak clock behavior. On the other hand, there are examples. I have an example in my paper on equilibrium measures where, in fact, on the AC spectrum, the density of states does not exist, where it proves there are at least two limit points, and you can actually prove the set of limit points of the density of states is a connected set. So if there are two, there are a lot. But in that case, it would be very interesting to, and if someone wants during the question period, I can tell you what the example is. It's a very simple example. It would be very interesting for this example to know whether you have this weak clock behavior. You certainly can't have strict clock behavior because there's no density to converge to. Okay, I'm next going to describe the main theorems in our paper. There are 5 in all, and then I'll try to say something about the proofs. And to state the first theorem, I need a definition, which is almost a standard definition. We add one extra condition. So it's what I mean by a Lebesgue point for the measure mu. So basically, I mean a Lebesgue point for the weight in the classical sense of Lebesgue, that the average of the weight over an interval with absolute values goes to 0. The 2 extra conditions is I only want to consider points where this average weight is positive. And second of all, I want the, it's partly cloudy in Los Angeles. I want the singular part to have no density. The singular part, for Lebesgue almost every x naught, this goes to 0, and for almost every x in the support of the singular, in the singular, not the support, in the singular with respect to the singular measure goes to infinity, but almost every point in the essential support of the AC spectrum is a Lebesgue point. So theorem 1 says the following. Suppose we have one of this set up with a general measure, and we have some point, which is the Lebesgue point for mu, and we have two conditions. So the first one is sort of complicated because of all the quantifiers. Forget about the quantifiers. It's basically saying, and in fact in the applications we don't need any of the quantifiers, is that if you make a perturbation by a complex amount, it's important that z is complex, then the kernel grows at most exponentially, uniformly in n. We have, uniformly in large n, we have an exponential bound. And as z goes to infinity, it's no worse than quadratic. And the second condition says if you take this diagonal, so let me perhaps remind you what this Kn is. I'll write it for the case where the arguments are equal. If you take this kernel, then if I wiggle the diagonal by an amount 1 over n, then this ratio goes to 1. I want it uniformly in A for A bounded. This we call the Lubinsky wiggle condition. In both his approaches, it's sort of the critical thing. He actually, in the first paper, uses Lubinsky wiggle plus the existence of a comparison argument and a very clever use of the Schwarz inequality to show how to get universality from the wiggle condition when you have a comparison object where you have universality. And in our case, we don't have in the ergodic case, we don't have a comparison object. But this is the key condition in both his approaches. And under these conditions, you have modified universality at x naught. So you need two conditions, exponential bound and Lubinsky wiggle. And if instead of allowing Gaussian z squared growth at infinity, you actually make exponential of z, then this is actually theorem, while not explicit, is implicit in Lubinsky's second paper, his second approach. And the result, as I stated, is in the paper of Avila Last and me. And our strategy, which I'm going to describe, is Lubinsky's in some sense, but the tactics we use and the particular proof I'm going to show you later of this theorem really is different from Lubinsky's. But we were certainly motivated by him. And while it's nice we could get the thing with the quadratic, only requiring the quadratic estimate, in all examples where one can verify this, you actually have an exponential bound without so Lubinsky's stronger hypothesis actually holds, and that's because there'll be a theorem later that explains why Lubinsky's hypothesis holds. Okay, so that's theorem 1. Theorem 1 says when you have exponential bound in Lubinsky, you get so 1 plus 2 implies modified universality. 3 is the condition that says this approximating rho n actually has some limit that I'll call rho infinity. And in this theorem, I really just need to know that the limit exists. I don't necessarily need to prove that it is the density of states. And I'll come back and say something about why I'm saying that in a moment. So that's condition 3. And theorem 2 says if I have a set of positive Lebesgue measure inside the absolutely continuous spectrum, and I have 3 plus 1, then 2 holes. So in Lubinsky's paper, one of his problems was he has this wonderful set of conditions. He has this wiggle condition, and then he says, unfortunately, I don't know how to prove the wiggle condition except in cases where my other method lets you prove universality. But I think it must hold more generally. And the more general is you really just need to control the existence of this limit. And obviously, as a corollary, if I have 1 and 3, then I have 1 and 2, and therefore I have not only modified universality, but universality because the rho ends are at least converging to this thing I called rho infinity. At least if rho infinity is the density of states or is the equilibrium behavior, I get clock behavior. So that's the second theorem. The third theorem involves the looking at the transfer matrix. The transfer matrix is the thing that updates the second order difference equation. It has become traditional to put an AN in the bottom component. In this audience, you're used to fixing AN equals 1. But with the choice, putting the extra ANs in the bottom component, you get matrices of determinant 1. So it's a little trick that... Anyhow, and the things on the other side are, in fact, the so-called second-kind polynomials. They're what you get by dropping the first Jacobi parameters and looking at the orthogonal polynomial for that. This third theorem says the following. Suppose I have some average boundedness of the norm in this sense of the transfer matrix at a point x naught, and I have a mild technical condition that the ANs are bounded from below. If the ANs aren't bounded from below, there's a theorem of Dombrowski that says there's no AC spectrum. This is exactly like what Tom and I proved that said if the BNs go to infinity, you have no AC spectrum. And Dombrowski used trace class perturbations. It's the same proof we had. She, of course, did it 10 years before we did. But so this to this audience is just a variant on Simon Spencer. But and you can call it Simon Spencer because you'd be using Arnold's principle. Then, in fact, you automatically have an exponential bound on the perturbations of the transfer matrix. So really, the step 1, if you know something at individual points on the spectrum, you automatically get control in this exponential. So the exponential bound is really equivalent to just boundedness at the initial point you're looking at. And there are very explicit constants. Okay, so that's...
I'm missing a 1 over n, so you have a 1 over n here, but in the other condition there was none.
Which there wasn't.
For the can, the original...
Yes, there was. Let's go back.
No, I mean 1 over n times can.
Oh, that's because that's wrong. There has to be a 1 over n. There's no...
I was confused at that point.
Okay, there's a 1 over n missing in that place in the slide. So that's wrong.
Where?
I mean, yeah, the theorem's correct because it's never true, but the hypotheses are never true. But in fact, in the theorem, I need a 1 over n here. Otherwise, there's no... Okay, so the next thing involves ergodic Jacobi matrices. Everyone here knows what that is. These slides were used for talks elsewhere. So basically, my A's and B's are samples of some ergodic process. And the example is almost Matthew. But again, I suspect this audience knows what almost Matthew is. And the spectrum in many of these cases are Cantor sets. And the fourth theorem says that for almost every omega in the sample space and almost every x naught in the AC spectrum, this limit exists and is positive. And lest you look at this and say, oh, it's a trivial use of an ergodic theorem. Well, there is an ergodic theorem here, but this is not, I mean, the KNs are not averages. While we're looking at some average of something, these P's don't have the right form to use an ergodic theorem in the usual way, so it's a more subtle ergodic. It's not a free use of the ergodic theorem, but it's connected with an ergodic theorem. So therefore, what we know is that by theorem 4, in the ergodic case, condition 3 holds. Condition 1 also holds by theorem 4, because if you can control the average of the P's and you can control the Q's are like P's, you can control the average of the Q's, then you've controlled the average of the T's. So basically, theorem 4 tells you that you have 1 and 3, and therefore you get clock behavior.
Sorry. Omega is referring to what in this?
Omega is going back to, we have an underlying probability measure. We have an underlying probability measure space. It's labeled omega. So we are looking at a family of Jacobi matrices. So in the case of almost Matthew, omega is the circle, and omega is just the angle on the circle. It's the phase. Yeah.
So the only thing you need is ergodicity, or?
You just need ergodicity plus being in the AC spectrum.
Okay.
Right? The theorem says almost every x naught in this support of the AC spectrum. Again, you don't need AC spectrum, but then it's an empty theorem. But just ergodicity and AC spectrum. This actually, in some sense, surprised me a little in that I certainly began thinking behavior might be different depending on Diophantine, almost Matthew, depending on the Diophantine properties of the rational number, and it doesn't. I mean, the theorems are true in both in the Diophantine case and in the Liouville case. Anyhow, it just uses ergodicity plus the AC spectrum. And the last theorem, so if you combine the earlier theorems, we get that the density, that you get clock behavior, but the density that arises is this limit of the 1 over n kns, and how could that not be the density of states? So if rho infinity is the AC part of the density of states, then in fact the limit in theorem 4 is given by what you think it's given by, namely when I multiply by W, the rho n converges to, this is the density of the absolutely continuous part of the measure, and that turns out to be more subtle than one might think, and I'll say something about the proof, I hope, later. So those are the theorems. Corollary is, in general, on the AC spectrum for general ergodic Jacobi matrices, we have this universality plus the and obviously the density in this case, which often lives on a Cantor set, is not continuous, let alone analytic or smooth. And so, right, there's no regularity needed on the weight. I obviously am not going to give complete proofs. Well, not obviously. They could be the proofs. None of the proofs turn out to be that hard, but there are enough theorems that I can't hope to show you complete details in my remaining 15 minutes. So let's first talk about the proof of theorem 1. The basic fact that, so this is the theorem that says that if I have exponential bounds and Lubinsky wiggle, then I get this universality. And part of this question is, what makes this sign kernel special? And in Lubinsky's work, it has to do with reproducing kernels and various other things, but we have a different way of looking at it that makes it particularly transparent, in my humble opinion. So, actually my opinion, I guess, is never humble. So the basic behind everything is the following. Suppose I have some function supported on an interval. Its L2 norm is at most 1, and its integral is the same as the integral for that would happen if f were identically 1. That in fact f is not identically 1, sorry. If f was a constant that saturated this, then in fact f is the characteristic function. So one way, if you have a characteristic function, you know the L2 norm and you know the L1 norm, and it saturates the Schwarz inequality, then of course you have equality. So this is a way, this is how to see you get the characteristic function. Elementary. Second version says the following. Suppose I have a function, I have an L2 condition on it, and its Fourier transform is supported on minus pi pi, and its value at 0 is 1, then f is the sine kernel, or sinc kernel, sine pi x over pi x. And this is just, you apply lemma 1 to the Fourier transform of f. So this kernel sine pi x over pi x enters because it's the Fourier transform of a characteristic function. The last condition is, instead of having a support condition explicitly, I have an entire function. It's L1, it's L2 norm along the intervals bounded by 1. It's 0 at 1. And instead of an explicit support condition, I have a condition on growth of f. Then again, I have the sinc kernel. And that's because I just take Paley-Wiener. The growth condition tells me so I'm done. OK. So this is actually going to let me prove the following theorem. Suppose I have an entire function on R. It has I have an entire function on the complex plane. It's real on the real axis. It has the L2 condition. It has this condition about 1. It makes life easy. It's actually not needed to suppose it's everywhere bounded by 1. And you have some a priori control on the zeros. So you know that the zeros are only on the real axis. And if you label them with z0 equals 0, which is not a 0, but you otherwise label the zeros like that, you know that the spacing between distant zeros grows essentially like j minus k. And you have this exponential epsilon. It's as they say in the lingo, it's of order 2 and type 0, I think. Then in fact, f is the sine kernel. And where does this come from? Well, I'm going to show you the proof when instead of this condition, I have an exponential condition. So this form, and because of what I call theorem 3, this sort of is always true, so this is no big deal. In general, you just use Fragment-Lindloff an extra time. Then in fact, you argue as follows. So f, because you have this exponential bound, you know by a Hadamard factorization theorem, f can be written in this way. The zeros are real, and this b is real because f was real on the real axis. So if we take z equals iy, then this factor, because zj is real, is of magnitude 1. This factor is of magnitude 1. This has this form. And so f of y is less than this product. And this product, the zj's, are essentially of distance j away. Now it's j minus 1, so that's why I have a y to the 4th. But the product is bounded by a sine sinh kernel. And so if you look at some proper object, you use Fragment-Lindloff, you actually see that you get this exponential growth and therefore apply the lemma. So just, again, the basic fact that's true here is if you know this condition on the zeros and this exponential bound, plus these other bounds, out pops the sinc kernel. Okay, so that proves theorem 1. Oh, sorry, that proves that this theorem. To get theorem 1, I let f of z, I look at this particular variant of the kernel. I fix a to be a real number, but instead of b, I take a plus z, where so b is now taken to be a complex number, and I want to normalize it about z, b equals a. I look at this ratio, and I look at points where this has a pointwise limit, because remember, you can take a subsequence, so you have a limit. So you look at a limit point. In the end, you prove the limit is what you think it is by showing every limit point is what you think it is. And by the bounds and some general compactness condition that tells you limit exists, you get a limit. By construction, f of 0 is 1, because if I take z equals 0, I get 1. By Cauchy-Schwarz, you get that f is bounded on the real axis. The fact that the reproducing kernel obeys this estimate, and that w is a Lebesgue point, and you can drop the singular thing, actually lets you get this L2 condition. Condition 1, which was this exponential bound, gives you the exponential bound on the limit. And there's a magic formula due to Markov and Stieltjes. They discovered it in 1885, independently at about the same time, because they were both answering a question of Chebyshev, who was Markov's advisors. This Markov, by the way, is the father. This is the Markov of Markov processes, but it's the father of the Markov of the Riesz-Markov theorem. So you have to keep straight who's who. And they got a spacing of zeros in terms of 1 over this kernel. And we know when you rescale everything, the Lubinsky wiggle condition is exactly what you need to get an a priori bound on the spacing of the zeros. And that's where we get the other condition, and so we get the same kernel. And this is Lubinsky's big idea, is using this Markov-Stieltjes inequality to make things work. Okay, I now want to turn to theorem 2. Theorem 2 said as long as I have pointwise convergence on a set of positive measure, then for almost every x, I get the Lubinsky wiggle condition. And since time is running short, I'm going to give you the next 2 slides in one sentence. Basic idea is one of Littlewood had 3 principles of analysis. Liouville's 3 principles of analysis is almost every function is almost a continuous function. Every convergent sequence of functions is almost a uniformly convergent sequence. And I'm forgetting his 3rd principle, but I need the one that's Egorof's theorem that says when I have pointwise convergence, then except for a set of very small measure, I have uniform convergence. And basically, if I'm in the set where things are converging, uniform limits are continuous, so if I make an error of order a over n, it doesn't change much. And so by Egorov, I know I have the wiggle condition as long as I'm at points that stay in the support, but I'm not in general at points that stay in the support. I could have a Cantor set, I can be in these gaps, but because almost every point is a point of density of Lebesgue measure, the size of the gaps is very tiny, and the exponential bounds turn out to give you bounds on the derivative that says over the part where you don't have control, you can't grow by much, and you put all that together and you get the Lubinsky wiggle condition. Okay, theorem 3. Theorem 3 was the theorem that said bounds on the average at a point imply this general exponential bound, and basically we just lifted an idea from the paper of Avila and Krikorian. They used ergodicity and other things in their proof, but it turns out those are not needed. And the basic idea is the following elementary fact. you start out with your transfer matrix, which is a sum of individual pieces. You look at the transfer matrix at a perturbed point, and it's a product of A's, and the two pieces of the transfer matrix, I remind you, has a 1 over an, z minus bn, an squared, 1, there's a minus sign there, presumably 0. If I vary z, all that happens is there's a rank 1 perturbation. So the norm of this perturbation is bounded by z over n plus 1, because I'm perturbing by n plus 1. And I do need, this is where the lower bound on the a's come in. And so there's a uniform bound of this form on the a's. And basically, you just take this combination, you futz around a little, and you easily get this bound. So it's really a very easy perturbation argument. And once you have this plus Schwarz inequality, you get this. So theorem 3 is really a very elementary use of the Schwarz inequality. Okay, now I want to turn to what we know in the ergodic case. In the ergodic case, we use what are sometimes called Diffie-Simon eigenfunctions. So Percy and I proved that for almost every x in the AC spectrum, with two-sided ergodic Jacobi matrices, there are solutions of the equation that are plane wave-like. The two are complex conjugates of one another. They're normalized by this Wronskian condition. Their absolute value is invariant. The phase in general is not. That's in some sense why one can't just say, oh, it's just the ergodic theorem, because we don't know a priori about the phases, and they're L2. So these are, this is just a translation of one of the theorems in our paper that many people have used since. But the important thing is it's known in the Diophantine case, for example, the phase is almost periodic. There is some invariance, but it's not in general, and one can prove it can't be. If that phase is ergodic, you can show the dual problem has only point spectrum, and since the dual problem doesn't, we know it's not always ergodic. And so this phase, but there exists a phase of this form, and the transfer matrix has this form, and so if you define B in the right way, you will discover that Tn has this magic form. The B's are really sampling your process, but these thetas are not. That's why you can't just use an ergodic theorem to get averages. But there is a lemma. I'm not even going to, again, time is running short. I'm not going to say a lot about it. But basically, one uses the fact that you lift up to the suspension. The L2 condition gives you enough regularity so that some object, after you make approximations, is equicontinuous. And you then use the ergodic theorem on the lift, and that gives you the existence of the limit. So it's as I said, you look at it right, it's not that hard, but it's a tricky argument because, in fact, the naive ergodic theorem you might try to use doesn't work. And I'm not going to tell you about the proof. So the last thing is theorem 5, and I want to try to explain what the issue is. So if we use the earlier theorems, we know that the zeros at almost every point in the AC spectrum, we know the spacing of the zeros is given by this limit, which I could call the microlocal density of states. If you use one of the theorems in Kotani plus Diffie-Simon, you can figure out the density of states is the ergodic average of the square of these Diffie-Simon wave functions. And if you futz around with what PNs are, you discover that this local density of states is an average of the imaginary part. So here you have the absolute value, but you notice there's a 2. Here you have the imaginary part. And so what you really need to know is the average of the imaginary part and the real part is equal. That is, you need to know that the average of the real part of the square of this presumably oscillating function is 0. And there's an argument that I can't give you even in the 5 seconds I have left. I see the chairman is being threatening. But there's a simple argument that lets you prove this, except at the very middle of the spectrum, which is exactly 1 point, so it doesn't matter. That proves theorem 5 and completes what I have to say.
Thank you very much. We now invite questions and comments on this topic.
So if you have that the Lyapunov exponent vanishes on an interval, do you think that the result would be strengthened in any way?
That what?
The Lyapunov exponent vanishes on an
Right.
interval.
Then what?
Whether you can strengthen the results in any way.
Yeah, I think you would probably be able to prove. I mean, you see, if the Lyapunov exponent vanishes, then you probably can already apply what's in the paper that Totic and I wrote. So I think you can probably prove that not only do you have universality, but it's uniform in the point and the interval.
Right, that was my question really. I mean, what are sufficient conditions under which you can prove?
So what Totic and I proved is that, well, you actually, for our arguments, you need a regularity condition, which you could perhaps dispense of using these ideas. So that's a global condition, but if you, for example, only have AC spectrum, then we know the density of states is given by the equilibrium. And in that case, as long as the weight is continuous and positive, you're fine, since we know that in the case you're talking about. And I have a feeling you don't need the regularity with what we're doing. So I don't think it's very hard. If you have an interval in the support, and if your weight is continuous and bounded from below, and then probably you can do it in general. But certainly in a situation where you have purely AC spectrum and you have some interval where the Lyapunov exponent is positive, then you're going to get uniform convergence just by using what Totic and I did, not using these methods.
Is the example which you briefly mentioned where rho n converges but doesn't converge to the density of
No. That's easy.
That's easy.
What's much more subtle is where the rho n's don't converge.
Okay.
That's the example. And the example is actually the following. So it's where you have AC spectrum and the rho n's don't converge. That their example, I mean, if you just take a, it's not hard to get examples where the density of states, if you have mixed spectrum, mixed AC and point spectrum in an ergodic problem, and there are examples of Sinai that has that, then the density of states will exist and will not be given by the equilibrium. Is there an eraser somewhere? Yeah, I see it. There's also one here. So the example in my paper is essentially the following. So I take minus 2, 2. I take my weight to be your favorite smooth function, Lebesgue measure on the middle. And I take dense point spectrum and the other piece. And now I'm going to tell you where the points are and what their weights are. Not the points. The points are actually going to be all the dyadic rationals. But I'm going to tell you what the weights are. And so you take some sequence of numbers that grows really fast. Say like that. And when your n And each dyadic rational is it can be uniquely written as an odd number over 2 to the n. So I look at the n in there. And when that, so 2 to the k, when that k in the dyadic rational is between an even and an odd, then the weights are 1 over 2 to this underlying 2 to the k times the, say, k squared to make everything summable. But it's basically pretty large. The total weight of all those points is of order 1 over k squared. And when I'm in the other intervals, it's e to the e to the e to the minus k. So on a given energy scale, either these points don't matter at all, or they're doing their best to mock up Lebesgue measure. And what you can show is if you look at orthogonal polynomials where the n is in one of these intervals, you basically think you're living on something where you really have Lebesgue measure on the interval minus 2, 2. And for those points, you can show the density of, if you take a sequence of n's through there, the density of states converges to the equilibrium measure for minus 2, 2. But now you take an n that sits in the middle of these intervals where the pure points don't matter, and then the polynomials think they're living on an interval of minus 1, 1, and the limit is in fact equilibrium measure for the smaller interval, so there are subsequences where you converge to these two different limits. Okay? And so that sort of says it's certainly not true that AC spectrum implies the existence of the density of states, so you can't have, in general, AC spectrum implies strong clock behavior, but this weak clock behavior could presumably still hold, and it would be very interesting in my opinion. Actually, it's hard for me to imagine proving it in this case and not doing it in general. There must be a general effect here. Or it would be interesting to show it doesn't. You don't have clock behavior. But I do think clock behavior holds every time you have AC spectrum.
Well, I propose that we thank Barry once again. Call the next speaker to take the stage.